Hello, and I would like to welcome you all to this interactive TA session. Good evening, I am Shankar. I am a PhD scholar working in the Department of Chemical Engineering, IIT Madras, and I'll be your teaching assistant or TA for this course. Just one second, let me take care of a couple of meetings first. Yeah. So, as I was saying, I'll be the TA for this fluid and particle mechanics course. This course is offered on the SWAYAM website by just powered by NPTEL, and this is a 12-week course. So this contains basics of fluid mechanics, some topics related to fluidization, particle bed, and some topics related to colloidal systems, colloidal assemblies as well. So in these sessions, we will be having a doubt clearing session where you can ask questions, and I'll be ready to clear your doubts. And you can also ask questions in the SWAYAM website by moving on to the, as you can see here, you can move on to the website. You'll be required to sign in, which I have signed in over here, and you can type in the course details. You'll be able to see where the courses are available. If you are registered for this course, you can join by clicking on the join button, or if you already registered, you can just click on the go to course option. Here you'll be able to see the weekly lectures. So for this week we have fluid statics, Newton's law, equation of continuity, equation of linear momentum, and quiz and tutorials. So the difference between these tutorial and quizzes, the tutorials are actually live recordings of a previous of the last time it was offered, and it just contains questions solved by other TAs in the previous years. In the practice assignment, there are some practice assignment. These are just tutorial questions that are random questions that are being given, which are not graded. But these quiz week one assignment questions, quiz week two assignment two questions will be graded. So you need to you need to practice on this first, and then attempt the quiz in a serious manner. The last date of the quiz is given as, for the first week is given as, I think, 9th of August, and each subsequent assignment will be having a deadline 1 week after that. So if you have any, that you can available, you can check for books and the audio transcripts, the text transcripts from that appear here. You can download them and read them if you like, if you want. And so till now, 2 weeks of lectures, tutorials, and quizzes have been uploaded. In the week 2, will be dealing with Bernoulli equation, Navier-Stokes equation, and cylindrical coordinate systems. An introduction to the cylindrical coordinate systems. So you can ask a question if you have any doubt. You can click on the ask a question here. You'll be redirected to Google Groups page. I believe one of the questions have already been asked. Still may have not gone through that. So one of the questions asked here is, I have a question about what is happening with videos. I have a clarity about the manometer, but how to calculate when there are different types of manometers. Like, I'm going to explain that in the lecture today. I'll show you how different manometers can be used to calculate the pressure. Over here, we'll have a simple YouTube manometer. We'll have a YouTube manometer with reservoir. We'll just have a system with which does not even look like a manometer, but still can be used to estimate the pressure at 2 points. So I'll reply over here as well once I have uploaded the video. And yeah, so that's all I have to say regarding this platform that is being given for discussion on questions related to the topics that you have seeing here.
Yeah, you
You can also get
weekly updates and assignments on this page where people can
and
you'll
will
be
be
getting
getting
assignments
assignments
and
and
practice and lectures
lectures
that
that
have been
have been
uploaded.
uploaded.
I think
I think
the
the
enrollment date
enrollment date
etc.
etc.
also will
also
be
will be
available.
available.
So you
So
can
you can
the
the
meeting link
meeting
that
link that
is
is
available is
available is
shown here.
shown here.
Unfortunately, I
Unfortunately,
am
I
I won't be
I won't be
available on
available on
Monday on
Monday
July
on July
31st,
31st,
but
but
otherwise I'll be
otherwise I'll
there
be
on
there
every
on
Monday
every
from
Monday
6
from
p.m.
6
to 8
p.m. to
p.m.
8 p.m.
Except for
Except for
this week
this week
will
will
be
be
held
held
on
on
Saturday on
Saturday on
29th of
29th of
July.
July.
I'll
I'll
upload this
upload this
recorded
recorded
session
session
on
on
the
the
drive
drive
that will be
that will
made
be
public
made public
to all
to
the
all the
students enrolled
students
for this
enrolled for this
course.
course.
Now, having
Now,
said
having
that, I
said
have
that, I
not
have not
yet
yet
started with
started
any
with
of
any of
dealing with the
dealing with the
questions.
questions.
If you have
If you
other
have other
questions
questions
related to
related to
the
the
subjects, I'll be
subjects,
happy
I'll
to
be happy
answer.
to
If you are
answer. If you are
attending these
attending
core
these core
classes,
classes, if
if you are
you are
unable to attend
unable
the
to attend
classes,
the
you can
classes,
just
you can
ask a
just ask a
question here,
question
as I
here,
was
as I
saying.
was saying.
Now,
Now,
let
let
me get
me get
to the
to the
discussion that
discussion that
we are
we are
going to
going
have
to
now.
have now.
So
So
this
this
week,
first
as
week,
we were
as we were
saying,
saying,
we are
we are
dealing with
dealing with
several
several
topics over
topics
here.
over here.
In fact,
In fact,
four
four
topics to be in
topics to be in
particular.
particular.
Starting with
Starting
the
with the
fluid
fluid
statics, which
statics, which
deals with
deals with
fluid at
fluid at
rest,
rest,
which
which
generally
generally
mainly
mainly
deals with
deals
pressure
with pressure
measurements.
measurements,
And
and
also some
some
questions
questions
we
we won't
won't
be
be
dealing
dealing
with
with that
that
here,
here,
but
but
also
also
there can be
there can be
questions on
questions on
capillarity
capillarity
and
and
rise of
rise of
liquid level
liquid
when
level when
when
system
a
when a
glass or
glass
a
or a
glass tube
glass
is
tube is
inserted into
inserted
a
into a
beaker
beaker
containing
containing
a
a
fluid and
fluid and
questions like
questions
that.
like that.
The
The
second
second
topic
topic
of
of
discussion is
discussion
the
is the
Newton's law of
Newton's law of
viscosity,
viscosity,
which
which
is
is
basically
basically
rheology.
rheology.
And
And
from here
from here
onwards, I
onwards,
think
I
we'll be
think we'll be
starting the
starting the
fluid
fluid
kinematics,
kinematics,
which
which
deals with
deals with
fluid flow
fluid flow
problems.
problems.
So
So
Newton's law of
Newton's law of
viscosity just
viscosity
deals
just
with
deals with
rheology,
rheology,
or
or which
which
is
is
just
generally referred to as
referred to
the
as the
study
study
of
of
flow
flow
or flow
or flow
patterns, or
patterns,
whatever
or
it is that
whatever
you
it is
want to
that you
call
want
it.
to call it.
And
And
the
the
third
third
part of
part of
discussion
discussion
that
that
happened
happened
during this
during
week
this week
was
was
on the
on the
equation of
equation of
continuity in
continuity
the
in the
Cartesian
Cartesian
coordinates and
coordinates and
equation of
equation
linear
of linear
momentum
momentum
in
in
the
the
Cartesian
Cartesian
coordinates.
coordinates.
So in
So in
every
every
case, in
case, in
any
any
system that you
system that you
consider,
consider,
any
any
non-nuclear
non-nuclear
system,
system, let's just say, take that example,
any
any
non-nuclear
non-nuclear
system you
system
take an
you take an
exam,
exam,
you
you
consider
consider
the
the
equation of
equation of
continuity
continuity
is
is
satisfied
satisfied
because of
because of
one
one
basic
basic
principle,
principle,
and that
and
comes
that
from
comes
the
from the
conservation of
conservation of
mass.
mass.
So in
So in any
system,
system,
mass will
mass will
always
always
be
be
conserved.
conserved,
And
and
we can
we can
also say
also
the
say
same
the same
about the
about the
conservation of
conservation of
linear
linear
momentum.
momentum,
Or we can
or we
even
can
say
even
that
say that
conservation of
conservation of
momentum for a
momentum for a
matter.
matter.
Now
Now will be
the
the
lectures have
lectures have
provided
provided
sufficient
sufficient
information on
information
how
on how
this
this
come
come
into the
into the
picture,
picture, but
all the
all the
lectures do not
lectures do
talk
not
about
talk about
what
what
or
or
how to
how to
solve the
solve the
questions
questions in
general
general
engineering
engineering
problems.
problems.
So in
So
these
in these
sessions, we'll be
sessions, we'll be
solving a lot
solving a
of
lot of
numericals, maybe
numericals, maybe
application
application
questions,
questions,
some
some
special
special
derivation if
derivation if
required,
required,
particular
particular
problems
problems
related to
related to
engineering and
engineering
fluid
and fluid
flows,
flows, and other such discussions. But we won't be touching through whatever that was already discussed in class. We won't be going through in detail what is discussed, what is told in the lecture videos uploaded on NPTEL. And having said that, we'll start with a few numericals. We'll start with, I have around 15 to 20 problems here that we can do, that we can solve during these sessions. If you have any other questions, please feel free to put them forward. I am available to discuss, and I am available to discuss, and I'll try my best to solve them as well. If you are still facing problems, I can take an effort, talk to the faculty, Professor Sumesh and Professor Basa, well, I know them personally enough to and communicate with them to clear out any other questions. So let's get started with a question on fluid statics. We have a mercury manometer, which is a pressure measurement device. Please excuse me for a second. Hello? 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 Yeah, sorry about that. I think someone was trying to join here. Yeah, I think the reminder or the problem solving session reminder just went out right now. So hopefully a few more people will join. Right now the audience is actually at 0. So let's start by solving a question on manometers. A mercury manometer, which this mercury manometer refers to the fluid inside the manometer, manometer's limb, and that is connected with a density of, let's say, 13,600 kilogram per meter cube, is connected to an air duct to measure the pressure inside. The difference in the manometer levels is 15 millimeter, and the atmospheric pressure is 100 kilopascal. Judging from the figure given here, determine if the pressure in the duct is above or below the atmospheric pressure. So what the first part of the question is, just by looking at the figure, we need to figure out, we need to understand whether the pressure in the column is greater than or less than the pressure in this column is greater than or less than the atmospheric or the atmospheric pressure. Yes. So what we need to understand is that the limb that is shown here, it is not closed, it is kept open. And when it is kept open, we always need to assume that the pressure at this point is the atmospheric pressure. And the atmospheric pressure the atmospheric pressure has several units. Let's write it in the standard SI units. That's 101.325 Pascal, which is 101.325 kilopascal, which is 1 atmosphere, which is 1.01325 bar, which is 76 centimeter mercury, which is 760 millimeter Mercury,
which
which
is
is
also
also
equal
equal
to
to
76
76
torr,
torr,
and this
and
is
this is
Torricelli
Torricelli
actually.
actually.
Yes.
Yes.
So as I
So
was
as I
saying, the
was saying, the
pressure at
pressure
this
at this
point
point
is
is
assumed to
assumed
be
to be
atmospheric
atmospheric
pressure.
pressure.
So
So
what we
what
need
we
to
need to
see
see is
is that
that
the
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 pink
pink
fluid
fluid
in the
in the
limb
limb
is in
is
fact
in
the
fact the
mercury,
mercury,
and we can
and
see
we can
that
see
the
that the
mercury over
mercury over
here and
here
here,
and here,
the
the
mercury in the
mercury in the
left
left
limb, which is
limb, which is
connected to the
connected
air
to the air
duct,
duct,
is at
is
a
at a
lower
lower
point
point
than the
than the
mercury in the
mercury in
right
the
limb,
right
which
limb,
is
which is
connected to
connected
or
to or
open to
open
the
to the
atmosphere.
atmosphere.
Therefore,
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 the
the
pressure
pressure
exerted
exerted
over
over
here
here
has to be
has to be
larger than
larger
the
than the
pressure
pressure
exerted here.
exerted here.
Otherwise,
Otherwise,
this height of the
height of the
mercury will
mercury
not
will
be
not be
lower than
lower
the
than the
height of
height
mercury
of
in the
mercury in the
right limb.
right limb.
Therefore,
Therefore,
judging
judging
from the
from
figure
the
1, we
figure
can
one, we
say
can
that
say that
the
the
mercury
mercury
level
level
in
in
left
left
limb
limb
is
is
lower
lower
than
than
the
the
mercury level
mercury level
in the
in the
right
right
limb.
limb.
Therefore,
Therefore,
pressure
pressure
in the
in the
column or
column or
yeah,
yeah,
sorry,
sorry,
pressure in
pressure
the
in the
duct
duct
is
is
greater
greater
than
than
the
the
atmospheric pressure.
atmospheric pressure.
This is
This is
because the
because the
only if the
only if
pressure
the
is
pressure is
greater here
greater here
can
can
this
this
height be
height
lower
be lower
than that
than
height.
that height.
This is
This
just
is just
a
a
simple
simple
observation that
observation
can be
that can
made
be
based
made
on
based on
this.
this.
Now,
Now,
the second
the
part of
second
the
part of the
question
question deals with
determine the
determine the
absolute pressure
absolute
in the
pressure in the
duct,
duct,
and
and
what
what
is
is
meant by the
meant by the
absolute
absolute
pressure
pressure
is
is
the
the
gauge or
gauge
the
or the
differential
differential
pressure
pressure
minus
minus
the
the
atmospheric pressure.
atmospheric pressure.
Basically,
Basically,
whatever
whatever
pressure you are
pressure you are
calculating here
calculating
and
here
here
and
alone.
here alone.
So,
So,
when you
when
take
you take
the
the
pressure
pressure
variation
variation
across
across
these
these
limbs,
limbs,
what
what
we
what we
do or
do
how
or
we
how
do
we
it
do it
is we
is
take
we
the
take
pressure
the
over
pressure over
here,
here,
and we
and we
assume that
assume that
the air
the
in
air
this
in
does
this
not
does not
contribute to
contribute to
much
much
pressure,
pressure,
or
or
the
the
yes, the
yes, the
pressure over
pressure over
here
here
by
by
air is
air
not
is
very
not very
strong,
strong,
and
and
this
this
part of
part of
mercury,
mercury,
the
the
mercury over
mercury over
here
here
and
and
mercury over
mercury
here
over here
exerting equal
exerting
pressure,
equal
so they
pressure,
get
so they get
cancelled off.
cancelled off.
But there is
But
an
there is
unaware,
an
there
unaware,
is
there is
more
more
mercury in
mercury
this
in
part.
this
This
part. This
15
15
millimeter on the
millimeter on
right
the
limb
right
has
limb has
mercury
mercury
that is
that
not
is
there
not there
in
in
this
this
left limb.
left limb.
And
And
again,
again,
this
this
atmospheric pressure
atmospheric pressure
also
also
acts over
acts
here.
over here.
So when we
So when we
take
take
when you
when
write
you
down
write
the
down the
expression for
expression for
pressure here,
pressure here, we
we
start by
start by
going
going
from
from
left
left
to
to
right.
right. If
If
we
we
are
are
on a
on a
limb
limb
that is
that is
looking
looking
downwards,
downwards,
we
we
generally
generally
add the
add the
pressure.
pressure.
If it
If
is
it
in a
is in a
limb that's
limb
looking
that's looking
upwards,
upwards,
we
we
subtract the
subtract the
pressure.
pressure.
Therefore,
Therefore,
we
we
start with
start with
pressure
pressure
A,
A,
which is
which is
acting
acting
in this
in this
direction.
direction.
So that
So
is
that is
PA
PA
plus.
plus.
Now,
Now,
assume that
assume that
the air
the
in
air in
here
here
does not
does not
contribute to
contribute to
a pressure
a pressure
difference over
difference
here.
over
If
here.
it's
If
like
it's like
some
some
other
other
oil or
oil or
something,
something,
we
we
have
have
to
to
consider
consider
this
this
height
height
as
as
well.
well.
There are
There are
questions will
questions
come to
I'll
that
come to that
afterwards.
afterwards.
Then
Then
this
this
and
and
this
this
point are
point
in
are in
equilibrium. That
equilibrium.
means
That
that the
means that
pressure
the
over
pressure
here
over
and the
here and
pressure
the
over
pressure
here
over
are the
here are
same.
the same.
So
So we'll be
calculating a
calculating a
pressure
pressure
from here
from
to
here to
here.
here.
We'll be
We'll be
adding that.
adding that.
And at the
At
same
the
time,
same
we'll be
time, we'll be
subtracting the
subtracting the
pressure that
pressure
is
that is
from here
from
to
here
here.
to here.
Therefore, in
Therefore,
effect,
in effect,
this
this
part
part
does not
does not
contribute to any
contribute to any
additional
additional
pressure.
pressure.
And we can
And we can
consider
consider
this part
this
to
part to
be the
be the
negative of
negative of
rho,
rho
the
the
mercury,
mercury
times
times
G
G
times
times
Hg.
Hg.
I'm just
I'm
writing
just
that
writing
as
that as
this
this
15
15
millimeter
millimeter
distance I've
distance
just
I've
written
just
down
written
as
down as
Hg.
Hg. and we know that this pressure over here is acting in this direction, that's in the opposite direction, and therefore PATM, and we equate that to 0 over here. And this pressure as OGH is explained well in the lectures by Professor Sumesh. And from here we can easily find out what the value of PA is. So we can write PA minus 13,600 times 9.81 times HSG is 15 millimeter. In SI units it will be 0.015 meter minus pressure at the atmospheric pressure, that is 101.1325 Pascal. Therefore, the pressure here will be is equal to the sum of these two terms. So I'll give you guys a minute and I'll wait for you so that you can solve it. So when you solve this, you'll get the value as 102. Yeah, 102,000 Pascal. Which is 102 kilopascal. Yeah. Moving on to part C, we have to repeat the problem for a differential mercury height of 30 millimeter. Now all we have to do is we have to change this 15 millimeter into 30 millimeter. Otherwise, and there is no change in the equations, as you can see here. There is nothing much has been changed. Only the value over here has been changed. So it's a very straightforward problem, and we can solve that by just substituting the value of 0.03 instead of 0.015 here. And yeah, so if you evaluate this is just very basic arithmetic maths. You can do this on your own. You will get the value as 104 kilopascal here. For those of you who are just joining now, am I audible to you? Okay, these lectures will be made available on the announcement platform on the Swayam. Over here, Okay, let's move on to the second question for this week. We are right now still dealing with pressure measurement or use of manometers and static fluids or fluid statics right now. Let's move on to the next question, where it's given that blood pressure is usually measured by wrapping a close air-filled jacket equipped with a pressure gauge around the upper arm of a person at the level of a heart. Using a mercury manometer and a stethoscope, the systolic pressure, which is the maximum pressure when the heart is pumping, and the diastolic pressure, the minimum pressure when the heart is resting, are measured in millimeters of mercury. The systolic and diastolic pressures of a healthy person are about 120 and 80, respectively, and are indicated as 120 by 80. The maximum blood pressure in the upper arm of a healthy person is about 120 millimeter mercury, as it was told before. If a vertical tube is open to the atmosphere, is connected to the vein in the arm of a person, determine how high the blood will rise in the tube. Take the density of blood to be 1050 kilogram per meter cube. Now, how do we solve such an application question? This is just a simple application of the manometers or the pressure fluid statics. So let's assume a person. Let's assume that he or she may be lying down, and this is ground zero. So his or her arm is connected to a manometer or a vertical tube that is open to atmosphere, and what we need to find out is the level to which the blood rises. We can assume that this horizontal distance over here is negligible. I just drawn that for the sake of understanding. We just need to find out, let's say, this blood H, which is the height to which the blood rises. So what we can understand from the question is that the maximum, if the vertical tube is connected to the, so the maximum blood pressure in the upper arm of a healthy person is about 120 millimeters of mercury, and this means that pressure does not actually mean, this does not actually mean that pressure as a unit of length or distance or millimeters. It means that the height to which mercury rises is actually 120 millimeters. So if you apply a pressure that can push mercury to a 120 millimeter height, that is a pressure that is there in our blood, in our blood vessels or by the heart. So therefore, the pressure measurement device, which is generally known as a sphygmomanometer, it's very it's the device that is used to measure blood pressure. So we can say that it has a pressure, the human body has a pressure of 120 millimeter mercury. Now, what is this in the SI units? So we know that rho times G times 120 millimeter mercury is actually the pressure that's available, and the rho here is the density of mercury, and therefore the pressure can be evaluated by just equating, just multiplying the density of mercury as 13,600 times G times the value in SI units, which is 0.12 meter. And this is the pressure in SI units. This is the pressure in Pascal that is exerted by our body on the by our heart. And if you have to measure, if you connect the heart, if you connect a vein, if you connect the tube to the vein, we have to measure how high the blood will directly go rather than pushing the mercury out. And we can calculate that by just equating the density of blood times the G times, let's say, the H blood to be equal to the pressure that's over here. Therefore, we can find out the blood by the height to which the blood rises, and the density of blood is given as 1050 kilogram per meter cube. I can wait for a minute for you guys to solve it. I'll give the answer out in a minute. If you have any questions, please feel free to ask. Yeah, so the value comes out to be approximately 1.55 meter. Now, if you connect a tube to the veins of a person, the blood will rise to a height of 1.55 meter. Therefore, there are some cases where you may need to connect a syringe to or a tube to the veins, especially when you are having some and when you can't consume food, solid food. You'll be having an in vitro connection to directly to your veins, where glucose is passed into your bloods. And you can see that the glucose bottles are actually kept at a height of at a considerable height as compared to where we are on the ground, when we are lying on the ground. And that is mainly because if you just connect it and keep it outside, blood will start actually may start for going back. So in order to avoid that, we the glucose bottles are generally raised and then kept on besides the person who is getting injected. Okay, we'll move on to the next question. It's on multi-limb manometer, which is characterized by the multiple limbs on connected between 2 points. So the question is, fresh water and seawater are flowing in parallel horizontal pipes. So what is shown here is actually the cross section of a pipe. The pipe may be like this, such that these 2 points are taken somewhere from the pipe or the pipeline. So, and they are connected to each other by a double U-tube manometer as shown in the figure. Determine the pressure difference between the two pipelines. Take the density of seawater to be 1035 kilogram per meter cube. Can the air column be ignored in the analysis? So air is given over here, and let's assume that the density of air is 1.05 kilogram per meter cube. repeat the okay, let's come back to let's come to the second part of the problem after we have completed here. So as I was telling before, we start with one part over here. We add whenever we are going, we add the pressure whenever we are going down, we subtract the pressure whenever we are going up. Whenever we see that the levels over here are matching, we generally disregard that. So the mercury height from here to here and here to here are disregarded. Similarly, air pressure from here to here is disregarded. Let's start from the left. We know that the pressure of fresh water plus, since we are going in downward direction, we have a rho of fresh water times G times H of fresh water, and H of fresh water is in fact this 60 centimeter given here. Now since this is lower than this, we disregard this much part. Therefore now we have come to here, it's in the opposite direction, the upward direction. We subtract it, and the fluid here is mercury times G times the height associated with the mercury, that's 10 centimeter. Now there is an air column for 70 centimeter, so that's again opposite direction or upward direction. Rho air G H air, and H air is 70 centimeter. Now we can disregard the pressure at these 2 points since they are in static equilibrium. Therefore we can go downwards in this point onwards and add the salt water or seawater pressure in seawater's pressure in this limb over here. So that's given by density of seawater times G times height of the seawater, and we can equate that to the pressure at the right side. If this is open to atmosphere, if this is kept open, we just have to take it as equal to atmosphere. So since it is connected to a pipeline, we have to consider that as the pressure of at that point as the pressure of the seawater in the pipeline. I hope this convection makes sense, and if there are any questions, please let me know. So once you have formulated the this part of this equation, the rest of the solution becomes very easy and straightforward. All you need to do is substitute the values, and what we need to find out is in fact the pressure difference between the two pipelines, and the pressure difference between the two pipelines is found out by PFW minus PSW, which is again just G times rho rho Hg Hg plus rho air H air minus rho F HF minus rho S H S, and all of these values are given. G is 9.81. The mercury density is 13,600. The mercury height here is 0.1 meter. Air density is 1.05 kilogram per meter cube. Air height is 0.7 meter. And similarly, the freshwater density is, we have to assume that it's 1000 or 995 or whatever, that close enough values you can take. And the height of the water is again 0.6. And finally, we have the density of seawater that is given here as 1035 kilogram per meter cube. So we have to use that value in only and times the height in the seawater column that is in this limb. So that is 0.4 meters. Now, if you do this simple mathematics, I can give you a minute to for you to solve it, but it's very straightforward from at this point. In fact, you will get the value to be roughly equal to 3.39 kilopascal. Please do confirm the same. The differential pressure will come out to be around 3.39 kilopascal. Okay, apparently the question is not yet over. Now we have to ask the question is, now we have found out the pressure difference. The next part of the question is, can the air column be ignored in this analysis? Let's just find out the pressure of the air column. That is P of air is equal to the density times the gravity times the height, which is 1.05 times 9.81 times the height of air in that column is 0.7 meters. And you can see that this value will be coming out considerably less than, I think around, it will come to around 7 Pascal, if I am not mistaken, approximately around 7 Pascal. And you can see that this 7 Pascal is considerably less than the 3,390 3,390 Pascal. That is the pressure difference between the 2 points at fresh and seawater. Therefore, we can safely neglect the pressure in the air column, since this is very much less than the differential pressure. Okay, it's still not over. There's still one more part of the problem that needs to be done. Repeat the problem by replacing air with a oil of specific gravity 0.69. So in this column, we just have to replace air with oil. The equation remains effectively the same. You don't need to assume that the height or something changes, because that's not given in the question. All you have to do is, all you have to assume is that air has been replaced. Instead of replacing air, instead of air, you'll get oil over here, and then solve the question. So the solution effectively remains the same way, by saying that delta P is equal to G times rho Hg Hg plus rho oil H oil minus rho freshwater H freshwater minus rho seawater H seawater. Again, if you put this equation as, if you try to solve this equation, you will get very simple answer. And the specific gravity of the oil is given as 0.69. That is, in the specific gravity is in fact the density of the fluid to the density of water at that temperature. So therefore, the specific gravity of oil is 690. If we can assume that water has a density of 1000, therefore the density of oil is 690, and the height of that oil column is 0.7. Again, the rest of the part remains effectively the same. Now, again, this can be solved, I think, very straightforward manner. You'll get the answer to be around 8.13 kilopascal. Again, please do verify it yourself. Please try to solve it on your own. If you have any doubts, please let me know. Yeah, we'll move on to the next question in a minute. I'll give you time for you to read the question and try to understand it. See if you can solve it out on your own. I don't know if it's R on the or not. Okay, I'm starting. Let's start with the next problem. Question number 4. The top part of a water tank is divided into two compartments as shown in figure 4. Now a fluid with so let's start with the next question. Question number 4. The top part of a water tank is divided into two compartments. So this is a water tank. It is compartmentalized into two, as shown in the figure. Now, fluid with an unknown density is poured onto one side, and the water level rises a certain amount on the other side to compensate for this effect. Based on the final fluid heights shown on the figure, determine the density of the fluid added. Assume the liquid does not mix with water. Just by looking at the problem, what all assumptions or what all can we make out from here? The first thing is that sorry about that. The first assumption we can make here is that whatever is given here, the liquid does not mix with water. That means immiscible fluid. Now, second assumption is that this liquid stays on top of the water over here that is present here. That means that the liquid density, or let's the fluid has a lower density than water. Otherwise, if at higher density, it would just sink or at least mix with, or get dispersed in water. Now, since that is not happening, we can safely assume that the density of the fluid is considerably less than that of water. Now, suppose this liquid was not there. Suppose this area was also filled with water. We'll be able to see the static pressure being equal at this particular level. Maybe not that level, but maybe at this level. But since this liquid is added, this water level has risen. Anyway, if you add a liquid over here, water level will never fall unless, it never will fall. So, since this is an unknown liquid that's added, the water level has in fact risen. So, what we need to do is to find out the density of the fluid. That's the question that's been asked. So, what can we how do we solve this problem? What we need to understand is all the points in the horizontal line over here are having the same pressure. Therefore, the water pressure over here and here will be the same, here and here will be the same, similarly here and here will be the same. Therefore, if you take this particular line, we can see that there is the pressure of this unknown liquid acting downward and the pressure of water acting here in this direction downward. And we can see that if we take a line that was over here, this particular line may be the pressure exerted by the unknown liquid and by the water in this particular box, in this particular volume, will be the same. In fact, the pressure exerted by this much fluid will be the same as the pressure exerted by this much fluid if we consider the bottommost part. And that can also be used to find out the pressure, find out the density over here. Let us consider this to be a U-tube manometer. In fact, we can do that way also, where we have a fluid from here that is balanced by the water over here. We have multiple ways to solve this way now. So what we can understand from whatever I've said till now is that the pressure of the fluid, let me compartmentalize this into, let's say, 1, 2, 3, 4 parts. So the pressure of fluid in 1 should be equal to the pressure of water in 3, and the pressure of the fluid in 1 and 2 will be equal to the pressure of the water in 2 and in 3 and 4. That also can be used. Therefore, the pressure of the hydrostatic pressure is simply given by rho times g times h. And if we put that for the fluid 1, we'll get the density of the fluid times g times the height of the fluid should be equal to density of water times g times height of water. And we know that if this much is 95 and this much is 50, we know that this much will be 45 centimeter. Therefore, from here we can easily find out the density of fluid, which is equal to, let's assume the density of water to be 1000 times 9.81 times 0.45, which is 45 centimeter, divided by, again, g times 0.8, 80 centimeter. Yeah, basically these two gets cancelled, so it's we'll finally get this as Well, 4500 by 8. And I think we'll get the value to be around 562.5 kilogram per meter cube. So yeah, this is a type of question where a tank is given rather than a manometer, and it is then compartmentalized, and one side is filled with the oil. And yeah, this is also a type of application of fluid statics and the pressure measurement here. Let's move on to question number 5 as shown in this figure here. Consider the system shown in figure 5. If a change of 0.7 kilopascal in the pressure of air causes the brine mercury interface in the right column to drop by 5 millimeter, the brine level in the right column, while the pressure in the brine pipe remains constant. Determine the ratio of A2 by A1. So what they have said is there is a system which has a reservoir like this that is connected to the column like this, which is then connected to a brine pipeline. Now what they have said is that there is a change of 700 pascal in this air. So if a change of 700 0.7 kilopascal in the pressure of air causes the brine level to drop by 5 millimeter. So that means that some air has left. Only when some air is leaving will there be a drop in the brine level, the right column. Therefore, let us assume that initially we had a system where I hope I've done a decent enough job of recreating the image manually. But yeah, let us assume that this is filled with air, this is filled with water, this is filled with mercury, and let's assume that this is the initial brine level. This has a specific gravity of 1.1. Yeah. So this is water, this is mercury, and yeah, this is brine solution. Now let us assume the heights of each case. Let us assume that this has a height HB1. So let us consider the initial tank here, and let us assume that the height of brine in the right limb is initially at HB1. Let us assume that the height of mercury in the right limb to be HG right 1. Let us assume that the mercury in the left is equal to HG left. And let us take let us take this to be H water. So if we write balance over here, we know that we'll be getting this would be H air
or
or
we can just directly take this
as
pressure at
pressure
A.
at A.
So you can write
So you
this
can write
as
this
the
as
air
the air
pressure over
pressure over
here
here
plus
plus
rho
rho
water
water
G
G
H
H
water
water
1
1
plus
let us assume that instead of assuming that
the height
the
at the
height
right
at the
and
right
left
and
limb is
left
like
limb is
that,
like that,
we can
we can
directly
directly
assume that
assume that
this
this
is
is
H1
H1
or
or
HHG1.
HHG1.
We'll get
We'll
this
get this
as
as
yeah.
yeah.
So
So
rho
rho
mercury
mercury
times G
times G
mercury
mercury
times
times
HHG1
HHG1
minus
minus H
B1
B1
should be, oh
should be,
sorry,
oh sorry,
minus
minus
rho
rho
brine
brine
times
times
G
G
times H
times H
brine 1
brine
is
1
equal to
equal to
the
the
pressure in the
pressure in the
brine
brine
pipeline.
pipeline.
Now let us
Now
assume, let us
let
take
us
the
take
same
the same
system.
system.
Let
Let
us
us
consider the
consider
same
the same
system here,
system here.
but
But
with one
with one
small
small
difference
difference
is that
is that
the
the
brine
brine
has gone
has
down
gone
by
down
5
by 5
millimeter
millimeter
because of
because of
the drop
the drop
in the
in the
pressure of
pressure
air.
of air.
That is
That
this
is
the
this the
PA1, this is
PA1, this is
PA2.
PA2.
We know that
We
the
know that
brine
the brine
solution
solution
is at
is at
actually
actually
as is at
as
the
is at
same
the same
the brine
the
pressure
brine
is at the
pressure is at
same
the same
value.
value.
The
The
brine pressure
brine pressure
remains
remains
constant
constant
is given.
is given.
So we don't
So
have
we
to
don't
write
have to write
PB2 here,
PB2
it's
here,
just
it's just
PB over
PB
here.
over here.
So because
So
of
because of
this
this
loss of
loss of
air
air
in the
in the
part
part
2,
2,
we see
we
that
see that
the
the
height of
height of
water
water
is in
is in
fact the
fact
same
the
because
same
water
because
does
water
not
does not
get
get
evaporated. Water
evaporated.
does
Water
not go
does
away,
not go
only
away,
air
only
has
air has
gone away.
gone away.
So height
So
of
height
water
of water
remains
remains
effectively the
effectively
same,
the same,
but
but
the
the
height
height
difference between
difference
the
between the
mercury
mercury
is
is
not the
not
same.
the same.
This value
This value
has
has
actually
actually
changed
changed
HHG2,
HHG2,
and as you were
and as
looking
you are
at
looking at
before,
before,
this would
this
be
would be
HB2.
HB2.
So now
So
if we
now
were
if we
to
were to
yeah,
yeah,
this would be
this
the
would be the
mercury
mercury
till
till
here.
here.
Now if we
Now
were
if
to
we were
write
to
the
write
pressure
the pressure
balance here,
balance
you would
here,
get
you would
that
get that
PA2.
PA2.
Here there is
Here there is
PA1,
PA1,
PA2
PA2
plus
plus
rho
rho
WG H1. Again,
WGH1.
water
Again,
does
water
not
does not
water height
water
does not
height does
change,
not
so it will
change,
be
so it will
H1
be H1
only,
only,
or it's
or it's
W1
W1
plus
plus
rho
rho
HG HG2
2
minus,
minus,
since
since
these are
these are
on two
on
limbs,
two
we have to
limbs, we have to
consider this
consider
as
this as
separately, left
separately. Left
one
one
here
here
and
and
here
here
as
as
rho
rho
HG
HG
G HHG in the
HHG in
right
the right
at 1.
one.
Yeah,
Yeah,
so we'll
so
get
we'll get
yeah,
yeah,
sorry about
sorry
that,
about
there
that,
was
there
some
was some
error here.
error here. Mm.
So yeah,
So
there
yeah,
is
there
no
is
left
no
or
left
right
or
limb
right limb
over here,
over
so
here,
we'll
so
get
we'll
that
get that
value,
value.
we'll get that
We'll get that
equation as we
equation
have
as we have
written
written
it
it
in the
in
first
the
place.
first place.
So in the
So in
second
the second
equation, we'll
equation, we'll
just
just
change
change
HHG2
HHG2
and
and
rho
rho
brine
brine
G
G
H
H
brine
brine
2 to be
2 to
equal
be
to
equal to
PP.
PP.
If we
If we
subtract
subtract
equation 1
equation
and
1 and
equation 2,
equation 2,
we'll get
we'll get
PA1
PA1
minus
minus
PA2 should
PA2
be
should be
uh,
uh,
these two
these two
terms. The
terms.
rho
The rho
GH
GH
of
of
water gets
water gets
cancelled,
cancelled,
but
but
this does
this
not
does
get
not get
cancelled. So it
cancelled.
will
So it will
be
be
plus
plus
rho
rho
HGG
HGG
times
times
delta
delta
HHG.
HHG.
Similarly,
Similarly,
the
the
brine level
brine
does
level
not
does not
also get
also get
cancelled. It will be
cancelled. It will
rho
be
B
rho B
times
times
G
G
times
times
HHBHB.
HHBHB,
And
and
the
the
pressure at the
pressure at the
right side,
right side,
in
in
fact,
fact,
does get
does get
cancelled. PB
cancelled.
minus
PB
PB
minus
should be
PB
equal
should
to
be equal
0.
to 0.
Therefore,
Therefore,
we get
we get
delta
delta
P should
P
be
should
equal
be
to
equal to
rho
rho
B
B
G
G delta HB minus OHG G delta HG delta HHG. We know that delta HB is equal to 5 millimeter, which is given by 0.005 meter. And therefore, if the brine solution has dropped by 5 millimeter, we also need to understand that mercury will also be dropped by 5 millimeter in the right limb. But that does not mean mercury will rise the same amount in the right limb. It just means that mercury, the volume of mercury that has changed will be the same. If 5 millimeter worth of mercury will be the same as the 5 millimeter mercury in the it will be equal to that in the same as the other limb. So here the area is A1 and here the area is A2. Therefore, if we write A1 times the we need to understand this is the same as the height of mercury in the here. So A1 times H1 or HHG or delta HHG in the left limb should be equal to A2 times delta HHG in the right. And we know that the reduction, the drop in height of mercury should be the same as the drop in height of the brine solution. Therefore, delta HHG is equal to the delta HHG in the right side. Therefore, we can write delta, but in the equation that we have shown here, this is actually delta HHG at the left. Therefore, we can equate and find out what is delta HHG in the left equal to. We can write this as A2 by A1 times delta HHG in the right. Therefore, again, this is total. Therefore, total delta HG should be equal to delta HG in the left plus delta HHG in the right, which is delta HHG in the right times 1 plus A2 by A1, which is just a combination of these two statements over here. Now, if we equate the two terms, and if you just substitute the values here, we'll be getting the answer here. We'll get minus 700 plus, since there's a drop in pressure, there's a negative sign associated with it. Otherwise, it will be the, yeah, so we'll get the point. 0.005 times 1 plus A2 by A1 minus 1100 times 9.81 times 0.005 is equal to 0. Now we can solve this equation that starts from here to here. You can just find out the values of A2 by A1, and in fact that is what is being asked in the question over here. Determine the ratio of A2 by A1. I'll wait for a minute to see if you are able to do this on your own, and if you still have any doubts, please let me know. You'll get the value of A2 by A1 as 0.13.
Okay,
Okay,
let's
let's
move on
move
to
on
the
to
next
the next
question.
question.
Okay,
Okay,
so
so
we have
we have
completed, or we
completed
have
or
done
we have
several
done several
questions
questions
on the
on the
static pressure
static pressure
measurement, or
measurement or
static fluid
static fluid
statics,
statics,
on
on
pressure
pressure
measurements
measurements
and
and
manometers and
manometers
other
and other
such
such
concepts, other
concepts, other
related
related
concepts.
concepts.
We are
We
moving
are
to
moving to two
two-dimensional.
dimensional.
We are moving to
Moving to
fluid
fluid
kinematics, which is the
kinematics, which is
study
the
of
study of
fluids in
fluids in
flow
flow
or
or
motion under
motion under
motion.
motion.
So
So
the first
the
topic
first
in
topic
that
in that
concept is
concept
the
is the
equation of
equation of
continuity.
continuity,
And in
and
the
in the
equation of
equation of continuity,
we have
we have
seen well
seen
how
well how
what is the
what is
difference
the difference
between a
between a
fluid being
fluid
called
being
as
called as
incompressible and a
incompressible
flow
and a
field
flow
being
field
called
being
as
called as
incompressible.
incompressible.
And
And
for
for
this
this
question, let us
question, let us
first go
first
through the
go through the
question now.
question now.
Consider the
Consider the
steady
steady
two-dimensional
two-dimensional
velocity
velocity
field
field
given by
given
vector
by
v
vector
is
v
equal
is
to
equal to
the u and
the
v
u and v
component as
component
given
as
by
given by
1.3 plus
1.3 plus
2.8
2.8
x
x
times i
times
cap
I cap
plus
plus
1.5
1.5
minus
minus
2.8 y
2.8 y
times j
times
cap.
j cap.
So the
So
u
the u
component of
component of
velocity is
velocity is
this, the
this,
v
the v
component of
component of
velocity is
velocity is
this.
this.
We just
We
have to
just have to
verify that
verify that
this flow
this
field
flow
is
field is
incompressible.
incompressible.
And when
And
we
when
say
we
that a
say
flow
that a
field
flow
is
field is
incompressible,
incompressible, what we
what we
have
to
to
assume is
assume
that
is that
uh,
uh,
it
it
follows the
follows the
continuity
continuity
equation.
equation.
And we
And
have to
we have
prove
to
that
prove that
the flow
the
field is
flow field is
incompressible. It means
incompressible.
that
It
we have
means
to
that you have to
assume
assume
that
that
the
the
density is
density is
constant.
constant.
And
And
when the flow is steady, since
steady,
there is
since
no
there is
time
no time
dependence
dependence
on u
on
and
u
v, you
and
have to
v, you
assume
have
that
to
the
assume that
flow
the flow
we can
we can
infer that the
infer
flow
that the
is
flow is
steady.
steady.
Therefore, a
Therefore, a
steady
steady
flow
flow
field
field
would have
would have
the
the
continuity
continuity
equation
equation
as
as
the vector
the
form.
vector
It will
form. It
have
will
del
have
dot
del dot
vector
vector
v should
v
be
should be
equal to
equal to
0.
0.
And
And
in the
in the
expanded form,
expanded
we'll
form,
get
we'll get
dou u
dou
by
u by
dou
dou
x
x
plus
plus
dou
dou
v
v
by
by
dou y
dou y
plus
plus
dou
dou
w by
w by
dou z
dou z
should be
should
equal
be
to
equal
0.
to 0.
So we just
So we
need to
just need to
prove that
prove
this
that
is
this is
correct.
correct.
We know
We
that
know that
there is no
there is
k
no
cap
k
term,
cap term,
so dou
so
w
dou
does
w
not
does not
exist, so
exist,
this
so
goes
this
to
goes
0
to 0
automatically.
automatically.
And we need
And
to
we need
find
to
out what
find
is
out what
dou
is
u
dou
by
u
dou
by
y
dou y
and
and
dou u by
dou
dou
u by
x
dou
and
x
dou
and
v by
dou v
dou y.
by dou y.
From here, it
From
is
here, it
very
is very
straightforward.
straightforward.
Dou by
Dou
dou
by
x
dou x
of okay,
okay,
let's write
let's
it down
write it down
anyways.
anyways.
You know that
You know
u
that
is
u
given
is
by
given by
1.38
1.38
plus
plus
2.8
2.8
x.
x.
V is
V is
1.5
1.5
minus
minus
2.8 y.
2.8 y.
So
So
here dou
here
u
dou u
by
by
dou
dou
x would
x
be
would be
differential of
differential of
the
the
term that's
term that's
shown above,
shown above,
which is
which is
2.8.
2.8.
Similarly,
Similarly,
dou v
dou
by
v
dou
by
y
dou y
will
will
be
be
minus
minus
2.8.
2.8.
Therefore,
Therefore,
dou u
dou
by
u
dou
by dou
x
x
plus dou
plus
v
dou
by
v by
dou y
dou
should
y
be
should
equal
be
to
equal to
0.
0.
This is a
This
very
is a very
straightforward,
straightforward,
simple
simple
problem that
problem
just
that
we need
just
to
we
just
need to just
understand what is
understand
meant
what
by
is meant
flow
by
field
flow
being
field being
compressible.
compressible.
And it only
And it
means
only
that
means that
the flow
the flow
field
field
should
should
satisfy the
satisfy the
continuity
continuity
equation.
equation.
And after
And
that,
after that,
the
the
application or the
application or the
solution of it
solution of it
is
is
very
very
easy
easy
and
and
straightforward.
straightforward.
If you have any
If you have
doubts,
any doubts,
please
please
feel free
feel
to
free
ask.
to ask.
Okay,
Okay,
let's
let's
move on
move
to
on to
the
the
next
next
question.
question.
The
The
u
u
velocity
velocity
component of a
component of a
steady
steady
two-dimensional
two-dimensional
incompressible flow
incompressible flow
field
field
is u
is
is
u
equal
is
to
equal to
ax square
ax square
minus
minus
bxy,
bxy,
where a
where
and
a
b
and
are
b are
constants.
constants.
Generate an
Generate an
expression for
expression
v
for
as a
v as a
function of
function
x
of
and
x
y.
and y.
So
So
the
the
u
u
velocity, which
velocity,
is
which is
given
given
by
by,
this,
let's
we know
we
that
know that
vector
vector
v in the
v in the
two-dimensional
two-dimensional
plane
plane
is
is
a
a
function of
function of
u and
u and
v.
v. and the u component of it is given by ax square minus bxy. Now it is a steady flow field, which means that there is no time dependence on any of them. It's a two-dimensional, which means only u, x, v, and y are required for this analysis. This is an incompressible flow field, which means the equation of continuity is satisfied. Therefore, we can rewrite this and we can try to solve it based on this assumption, the equation of continuity, that is given by dou u by dou x plus dou v by dou y should be equal to 0. And with that, we know that u is given by ax square minus bxy. So therefore, dou u by dou x is just a differential of dou by dou x, which is 2ax minus by. And we can substitute that here, such as 2ax minus by plus dou v by dou y should be equal to 0. And we can finally get the value of dou v by dou y should be equal to by minus 2ax. When we integrate this with respect to y, since this is a partial differentiation, we just need to focus on integrating y. We don't have to consider x as a function of y. So this would come to b times y square by 2 minus 2ax y plus a constant of integration. Now, what we need to understand here is one crucial thing. This constant does not generally mean an arbitrary constant. It is actually generally a function of x, because when you partially differentiate a term that contains only x with respect and x in it, and you partially differentiate a term with respect to y, and the term has only x in it, it goes to 0. Therefore, the constant does not necessarily mean that it is just an arbitrary constant or has a particular value. In fact, it can mean that it it is a function of x alone and not a function of y. Because it was a function of y, it would generally come out at that point. Since it's not a function of y, it goes to 0. And we can find these constants of integration only if the boundary conditions are provided. So the final expression for the v component of velocity is given by vy square minus 2axy plus any function of x, as shown here. Okay, another similar problem as to what we did right now. Two velocity components of a steady incompressible flow field are known. U is equal to ax plus bxy plus ey square, and b is equal to axz minus byz square. Generate an expression for w as a function of x, y, and z. Again, it's a flow field which is incompressible, and the only difference is that this is in the three-dimensional coordinate system. The third dimension has to be taken. So dou u by dou x plus dou v by dou y plus dou w by dou z should be is equal to 0. And we can see that u is equal to ax plus bxy plus cy square. Therefore, dou u by dou x refers to partially differentiating the u function with respect to x. We'll get a plus by plus 2 a plus by plus this will be 0, and we'll get v as axz minus byz square. Therefore, dou v by dou y should be equal to minus bz square, since the first term goes to 0.
Therefore, when you substitute these values, you'll get a plus by minus bz square plus dou w by dou z should be equal to 0, and we'll get dou w by dou z as bz square minus a minus by. Therefore, when you integrate this, we just can write this as bz cube minus az minus byz plus constant. But here it is not just a function of x or function of y alone. It can be a function of x or y together. In fact, it doesn't differentiate between whether it is a function of x or function of y. It can be a linear combination of x and y or any convoluted functions of x and y alone. As long as there is no z term in that f of x and y, when you partially differentiate that, it will go to 0. Okay, we'll take a break here for a minute, and I'll come back and we can solve the next question. I'll just show the question on the board. And yeah, this question is related to simple discharge and pipe related problems. It's a very direct question. See if you can try to solve it. Please give me a minute for two. Okay.
Okay. So
Welcome back.
welcome back.
We'll do
We'll do
one more
one more
question,
question,
and I think
and
we'll
I think
stop
we'll
for
stop
the
for the
session today.
session today.
So the
So
question
the
states
question
that
states
a
that
30
a 30
centimeter
centimeter
diameter
diameter
pipe
pipe
conveying
conveying
water
water
branches out
branches out
into two
into two
pipes
pipes
of
of
20 and
20 and
15
15
centimeter
centimeter
respectively.
respectively.
If the
If
average
the average
velocity in the
velocity in
30
the 30
centimeter pipe
centimeter
is
pipe is
2.5 meter
2.5
per
meter
second,
per second,
find the
find the
discharge in this
discharge in
pipe.
this pipe.
And what is
And
meant
what is
by
meant
this
by
word
this word
discharge? It
discharge? It
generally
generally
refers to
refers
something
to
known as
something
the
known as
flow
the
rate.
flow rate.
And we
And
know
we
that
know that
the
the
flow rate
flow rate
is
is
just
just
very
very
basically the
basically the
velocity of
velocity of
the
the
fluid
fluid
times
times
the
the
area
area
of
of
cross
cross
section.
section.
We are
We are
assuming that
assuming
the
that
area, the
the
fluid
fluid
occupies the
occupies the
entire
entire
area
area
and not
and
just a
not
part
just
of
a
it.
part of it.
So if
So
we
if
are
we are
doing it
doing
like
it like
this,
this,
the
the
discharge
discharge
in
in
or the flow
or the
rate
flow rate
in
in
the
the
pipe,
pipe,
let's say in the
let's say in
30
the 30
centimeter dia
centimeter
pipe,
dia pipe,
is given
is given
basically
basically
by
by
the
the
um, the
the
velocity in
velocity
that
in that
pipe
pipe
times
times
the
the
area of
area
cross
of cross
section.
section.
In a
In a
pipe itself,
pipe
we have to
itself, you have
assume
to
that it's a
assume that it's a
circular
circular
pipe.
pipe,
Very
very
straightforward
straightforward
assumptions here.
assumptions here.
And the
And
area
the
of
area
a
of a
circle is
circle
given
is
by
given
pi
by pi
times
times
d
d
square by
square by
4,
4,
where I'm just
where I'm
putting a
just
1
putting a
here
1
so
here
that
so
this
that
is
this
just
is just
referred to as the
referred to as the
first pipe.
first pipe.
So we'll
So
get
we'll
this
get
as
this as
2.5
2.5
times pi
times pi
times
times
30
30
centimeter is
centimeter
0.3
0.3
squared by
squared by
4.
4.
And in
And in
fact,
fact,
this is
this
very
is very
straightforward. We'll get
straightforward.
this
We'll get
as
this as
0.177
0.177
meter cube
meter
per
cube per
second.
second. Next,
Determine the
determine the
velocity in the
velocity in the
15
15
centimeter pipe
centimeter
if the
pipe if the
average
average
velocity in the
velocity in
20
the 20
centimeter pipe
centimeter
is 2
pipe is
meter
2
per
meter
second.
per second.
So what
So
is
what
the
is the
discharge
discharge
or what
or
is the
what is the
velocity in
velocity in
this
this
pipe
pipe
if the
if the
velocity in
velocity
this
in this
pipe is 2
pipe is
2 meter
2
per
meter
second?
per second?
So what
So
we
what
know
we know
is
is
the
the
velocity
velocity
itself does
itself
not
does
get
not get
conserved.
conserved.
Velocity
Velocity
does not
does
get
not get
conserved here.
conserved here.
But what
But
gets
what gets
conserved
conserved
is in
is in
fact
fact
the
the
flow rate
flow rate
or
or
the
the
mass.
mass.
So the
So the
mass of
mass
fluid
of fluid
here
here
will
will
be
be
equally or
equally
will
or
be
will be
distributed in such
distributed
a
in
way
such a
that
way
it is
that it is
conserved when
conserved
you
when you
add will
add
be
will
the
be
sum
the
of the
sum of the
masses
masses
distributed
distributed
in
here in
pipes 2
pipes
and
2
3.
and 3.
So
So
since this is
since
a
this is a
fluid or
fluid
since
or
this is
since this is
water, we can
water, we can
assume that
assume that the
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 we can
we
assume
can
that the
assume that the
density of
density
water
of
does
water
not
does not
change.
change.
Therefore, the
Therefore, the
volume does
volume
not
does not
change,
change,
or the
or the
volumetric flow
volumetric
rate
flow
that's
rate
coming
that's
in
coming
this
in
pipe
this pipe
that gets
that
split
gets
into
split
these
into
two
these two
is
is
effectively
effectively
the volume
the
of
volume of
water coming
water
in
coming
through this
through
pipe
this pipe
is
is
effectively the
effectively
sum
the
of the
sum of the
volume that is
volume
coming
that
in
is
the
coming
pipe
in the
2
pipe
and
2 and
3.
3.
Therefore, we
Therefore,
can
we
write
can
that
write that
Q1
Q1
is
is
equal to
equal to
Q2
Q2
plus
plus
Q3.
Q3.
And we
And
found
we
out
found
that
out that
Q1 is in
Q1 is
fact
in fact
0.177 meter
0.177
cube
meter
per
cube per
second.
second.
Now what
Now,
is
what is
Q2?
Q2?
We know
We
that
know that
that is
that is
again
again
equal to
equal to
V2
V2
times
times
pi
pi
D2
D2
square by
square by
4 or
4
V2
or
times
V2 times
A2,
A2,
which is pi
which is
D2
pi
square
D2
by
square by
4.
4.
And
And
this is in
this is in
fact
fact
2
2
times
times
pi
pi
times
times
0.2
0.2
square
square
by
by
4.
4.
And
And
yeah, you
yeah, you
can
can
find out
find out
this
this
value very
value very
easily.
easily.
I
I
Yeah,
Yeah.
and
And
Q3
Q3
should
should
be
be
therefore
therefore
equal to
equal to
Q1
Q1
minus
minus
Q2, which
Q2,
is
which is
0.177,
0.177,
sorry,
sorry,
0.177
0.177
minus
minus
2
2
pi
pi
times
times
zero point 0.2
0.2
square by
square
4.
by 4.
Therefore, you'll
Therefore,
get
you'll get
velocity at
velocity at
3
3
as
as
Q3
Q3
divided by
divided by
A3. We
A3.
know
We
that
know
Q3
that
is
Q3
equal to
is equal
V3
to
times
V3 times
A3.
A3.
Therefore,
Therefore,
V3 is
V3
equal to
is equal to
Q3 by
Q3 by
A3.
A3.
And
And
this we'll
this
get it
we'll get
as
it as
pi
pi
times
times
it's a
it's
15
a 15
centimeter
centimeter
diameter
diameter
pipe, so
pipe, so
0.15
0.15
square
square
by
by
4.
4.
and this would be 0.177 minus 2 pi into 0.2 square by 4.
Yeah,
Yeah,
this
this
is
is
the
the
answer that
answer that
you get
you
when
get
you
when
try
you
to
try to
solve for
solve for
V3.
V3.
Please let me
Please
know if
let me
you're
know if
having
you're
any
having any
trouble.
trouble.
Yeah,
Yeah,
I'm waiting
I'm
for an
waiting for
answer.
an
I'm
answer.
hoping to
I'm
get
hoping
it
to
from
get
you.
it from you. Hello. Hello. சொல்லுங்க. ஆமா 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 23 7 10 கிலோ ஆயிடுச்சு 3 கிலோ. அது செக் கேபின் பேக்கிங் வந்து 10 கிலோ வருது. இதுதான் பாடு, இதுதான் போய்டும். நான் கேட்டா அண்ணா ஓகே பரவாயில்ல செகண்ட் பேக்கேஜ் அவ்வளோக்கு பார்க்க மாட்டேன். பைசா இருக்கு அது ஏன்னா ஃப்ரெண்ட்ஸ் இருக்காங்க வந்து பார்க்கிறது அப்படியே இருக்கும். ஆமா 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 எங்க அங்கே இருந்தா அங்கே இப்போ 12 மணிக்கு போனோம். ஆமா ஆமா இல்ல அது சொல்றேன் நான் இப்பதான் பாக்குறேன். ஆமா நான் சரி சரி அதை பார்த்து மாறி ஓகே ஆல் தி பெஸ்ட் ஓவர் டு மாடல் இன் தி சேம். ஓகே தேங்க் யூ பை. ஓகே பை.
So yeah,
we'll
we'll
get the
get the
final
final
answer
answer
for
for
this
this
as
as
around
around 6.44
6.44
meter
meter
per
per
second.
second.
Yeah,
Yeah,
so there are a
so
few
there are a
more
few more
problems that
problems
I
that
have
I have
written
written
down, but
down, but
yeah, I
yeah,
think
I
we
think
can
we
do
can
one
do
more
one more
question on
question on
this.
this.
Oh no,
Oh
this will
no,
take
this
a
will
lot
take a
of
lot
time.
of time.
So we'll
So
keep
we'll
these
keep these
questions for
questions for
next week.
next week.
And
And
yeah,
yeah,
I
I
would
think I
like
would
to
like
thank
to
you for
thank you
your
for your
time and
time and
attention. If you have
attention.
any
If you have any
questions again,
questions,
please
again,
feel
please
free to
feel
let
free
me
to let
know.
me know.
I am
I
here
am
to
here
help.
to help.